Thanks everyone for joining the seminar, and I'm very pleased that we have Bikram Karmakar, who's from the University of Florida, and he's going to talk to us about evidence factors.
Thank you, George, for the invitation. Thanks, Lindsay, for setting it up. And thank you, everyone in the audience, for joining us today. So in this seminar, I'm going to talk to you about evidence factors, as George said. It's going to be a tool for internally replicate an observational study. And I'll tell you what I mean by that. But the purpose of this presentation is going to be three things. One, I'm going to give you an introduction to the topic. Two, I'll tell you how to implement it. And three, I'll discuss what you can learn from it. And throughout the presentation, I'll be using an example, which is the effectiveness of Catholic schools. But before all of that, let me quickly start with a short story. And this is a story about a fundamental constant. The fundamental constant here is the charge of a single electron. So as of 2018, actually starting 2018, the International Council of Science declared that charge of a single electron, which is denoted by E here, is known exactly. So what you see on your screen here, these numbers, every number on that is known exactly. There is no discrepancy in that. So this discovery or this calculation went back years. So over a century ago, in 1913, Millikan first calculated the number up to a reasonable precision. So he used his own equipment, which was called the oil drop experiment, and he calculated the charge of a single electron up to 6 times more precision than anything known before that. Okay? And Millikan was awarded the Nobel Prize in Physics in 1923 for his work on that. The citation read, for his work on elementary charge of electricity. So let's take a walk through for about 2 decades following that. So Millikan in 1913 calculates this number up to some uncertainty, and the scale you are looking at here is incredibly magnified. So it's about 10 to the minus 25 of that order. So he used the oil drop experiment, the most sophisticated equipment of that time, and even compared to, even in today's scale, it's pretty sophisticated equipment. And using that, not only he did calculate it, but many people in other groups, other research areas also used it to replicate his calculation. So for about 10 years, there are many corroborations of this measurement, following which he got the Nobel in 1923. The following year, 1924, Nobel Prize in Physics was awarded to Manne-Steinberg. So Manne-Steinberg was not interested in electric charge, so to say, but he was more skilled in X-ray spectroscopy. And Manne-Steinberg's student thought about a way to get to charge of electron E in a roundabout way through electron spectroscopy techniques. And he got a number which was way further than what Millikan and everyone else had calculated. The same year, 1928, Arthur Eddington, who is more popularly known today because of his the first confirmation of general theory of relativity, he did a completely theoretical exercise. He used a general theory of relativity and Pauli exclusion principle to calculate E and claim that E should be higher than what Millikan had calculated. So in the paper, Eddington writes, the discrepancy is about 3 times the probable error attributed to Millikan's value, and I cannot persuade myself that the fault lies in theory. So when he is talking about it, he means the theory he used, starting from general relativity and Pauli exclusion principle, he doesn't think that's wrong. Okay, so there are two conclusions you can make from that. One, there is something wrong with Millikan's calculation. Two, one of the theories, either general theory of relativity or Pauli exclusion principle, they are wrong. Then Paddington writes in a few paragraphs later that I have learned of a new determination of E by Steinberg, which is higher, that would and I understand that a higher value is obtained, which would closely confirm the present theory. So what is going on here? So you'll see that all of them are asking the same question: what's the value of E? And if you think about it, they're using very different areas of expertise, very different techniques to get to the same answer. And even though it didn't seem like it, the oil drop experiment, which was replicated by many, doesn't seem to be foolproof because it's not confirmed by the other techniques. So let me come to the conclusion of the story here. So Professor David Bailey in 2018 writes, quote, a series of beautifully consistent results had shared a common bias, and he's talking about Millikan's calculation and the calculations following it for a decade, that only became apparent when experiments were done by different groups using different methods. So what do we learn from it? We learned something very important. The current value is neither Millikan's value, nor Eddington's value, nor is Steinberg's value. The current value is even higher than all three. The current value is on the right over here. So we know, following the history, that Millikan's calculation was biased because of an incorrect calibration of viscosity of the air in the equipment. And the other two calculations were also slightly wrong, and they can be fixed if you look at it carefully enough. But how do we know today that what we know is absolutely correct? We know it because it is confirmed to a considerable extent by not just one method, but 4 different methods. 3 of them I talked about in the last slide. The other one comes from quantum mechanical calculations. And a big conclusion, big moral of the story is biases can replicate. Even if you don't know there is bias, biases can replicate. And if you know there is possibility of bias, the possibility that it will replicate is even higher. So when we talk about replication, it has its limits. Replication is an attempt to resolve the principal sources of uncertainty that linger from previous studies. There is little to no point in repeating a study if doing so produces the same uncertainty. And this statement might be a little strong, but I'll stand by it for now. Rather, a replication should eliminate or reduce or disrupt, or at the very least, it should vary a principal source of uncertainty in your study. And this is not something that's new to us, and it's been discussed previously by various researchers. For example, Marvin Susser said the epidemiologist seeks consistency of results in a variety of repeated tests. And also writes, the strength of the argument rests on the fact that diverse approaches produces similar results. All right, so Marvin Susser said that related to epidemiology, but similar statements were made much earlier than that. Charles Sanders Peirce writes, we should trust rather to the multitude and variety of arguments than to the conclusiveness of any one. Our reasoning should not form a chain which is no stronger than its weakest link, but a cable whose fibers may be ever so slender, provided they are sufficiently numerous and intimately connected. And you can find similar sentiment even before that in John Stuart Mill's writings. So this is sort of a thought exercise, and I give you a context to it. But what do we learn from that for us? We are interested in causal questions. We are interested in causal effect of some exposure on some outcome, and we are interested in observational studies. So let's focus on observational study. In an observational study, the principal source of uncertainty stems from the absence of random assignment. That is, the inevitability that adjustments for measured covariates may have failed to render comparable the treatment groups. Sorry, there is a comparable treatment groups being compared. So when you think about replicating an observational study, one seeks to remove or disrupt or at least vary some source of potential bias to determine whether observable effects of treatment appear or vanish. So thinking in this way, thinking application of an observational study in an attempt to remove or disrupt or vary the source of bias, we can replicate an observational study. So the purpose of this talk is going to be to give you a principal method. Principal method here will be called the evidence factors analysis, through which in an observational study we can provide varied and essentially independent evidence that becomes more difficult to attribute to bias because of its variety. Not only that, we'll be able to measure and quantify the resulting strengthening of evidence for an effect and against a bias. Okay. So different pieces of evidence factors analysis are going to be 4 pieces, and this slide is going to be my home slide. So I'll be coming back to this slide a few times to walk you through all these 4 points. So just to begin with, the 4 points are going to be comparisons that depend on substantially defined assumptions, assumptions whose validity, one of them might be invalid but does not essentially invalidate the other assumptions. Number 2, within the same observational study, the comparisons are statistically independent. 3, even when other comparisons are biased, the current test, the current comparison will still be valid and still be independent from possibly invalid other comparisons. And number 4, integrate the evidence you get from your analysis using evidence factors. So these will be my 4 points, but I'm now going to start talking about point number 2 and 3, because those are sort of technical questions. The technical question is it possible in an observational study, in a single observational study, that's asking a hypothesis, that's asking for testing a hypothesis, to create comparisons that are independent of one another in a meaningful way? And is it possible to create those comparisons which one of them can be biased and still be independent of an unbiased comparison? So let me give you an answer, and it's a short proof of the fact that you can create independent comparisons in one study. So think of a design where you have 3 treatment positions. I have numbered them 1, 2, and 3. You have 3 subjects, A, B, and C. So one of those subjects are going to take one of those treatment positions. So in this picture, I have showed A takes position 1, B takes 2, C takes 3. Suppose the hypothesis you are interested in is the treatment positions do not change the outcome of the subjects. So let's consider R1 in parentheses 3 to denote the rank of the subject in position 1 among all the 3 units. And R2 in parentheses 2 is the rank of the subject in position 2 among the subjects in position 2 and 3. So those 2 are denoted, or those 2 are illustrated in the picture above. So I'll show you in just a few lines of calculation, these two are independent in one special circumstances. And this is a simplification of Renyi's fundamental lemma in his 1962 paper. So consider the design where you assign everyone randomly. So you assign the subjects to the treatment positions in a random manner. Then under that assignment, if the hypothesis were true, then every possible value of the pair R13 and R22 will be equally likely. So in other words, you can write the joint probability distribution as follows. And if you take the marginal distribution from that, you will get the marginal distribution of R22 is a coin flip, because R22 can only take one of two values. And for the simplification here, everywhere, I have assumed there are no ties. So just one extra line of calculation will show you that R13 and R22 are independent of one another. Okay. So in this one slide and in this few calculation, I have assumed that you have randomly assigned everyone to the treatment positions. And I have concluded that you have two comparisons, two ranks. These are partial ranks which are independent of one another. Let's now suppose they are not randomly assigned. Suppose instead that after position 1 is filled, by randomly picking one of the three people, it is twice more likely of the remaining two, the higher one, the one with the higher outcome, will take position 2. Okay. If that happens, then under the hypothesis, the previous proof does not work because all possible values are not equally likely. Yet, we can show, and it's not hard to show, that probability that R13 equal to I still remains the same as before. The first comparison still remains valid. We can also show that if you look at the joint, it's still independent. Sorry, in other words, if you look at the joint distribution, it's still product of the two marginals. So the independence remains. So what is not true is R23 is no longer a valid rank test statistic according to the previous distribution. So what I showed you is in one design, you can find comparisons which are independent of one another and which can be biased in different ways, and biased comparison in one does not affect the other comparison. And the result can be generalized to a considerable extent so that it can be useful for our purpose. So for example, we do not need to think about just a sequential assignment. What is needed, and I won't expand on it, is one test statistic needs to be invariant under something and the other test statistic needs to be fixed under something. You do not need to use rank test. Rank test give you independence, but if you get rid of rank test and use your favorite some other test statistic, you still get near independence. And near independence is going to be sufficient. I'll discuss later in the talk. You can allow biased assignment not just in one of them. You can use biased assignment in both of them and still get independence. We can have more than two evidence factors. We can have more than two comparisons. And finally, it doesn't have to be so that you always use a part of the data for some of the comparisons. Okay. So I have discussed point 2 and 3 sort of in a technical sense, but let me now go back to point 1. and I'll connect the 3 dots, 1, 2, and 3 together in one study. So the question we're interested in is, are Catholic high school more effective than public high schools? So to test that causal question, we can use the testable implications where among comparable students, comparable in terms of various background characteristics, IQ score in high school, parents' education, income, etc. Catholic school students, okay, so I should be more precise here. So what we're interested in is, does Catholic school schooling has a higher income mid-career? So if that is true, then Catholic school students will earn more than public school students among comparable students. 2, being Catholic encourages you to go to Catholic school, which implies the students who are Catholic will earn more than students who are not Catholic. Number 3, so depending on where you live, geographical accessibility of Catholic school can encourage you to go to Catholic school. So that can be used living near a Catholic school can be used as an IV, which implies that growing up in areas where Catholic schools are more accessible will earn students more than comparable students not living near Catholic schools. Okay, so we'll create a study and we'll create 3 comparisons using these 3 testable implications, which are going to be evidence factors. And these 3 comparisons each of these 3 comparisons has been used and published in papers, not typically in the same paper, but we can do all of them together in a principled manner. So number 1, the first comparison is the direct comparison of Catholic to public school students. Now, what could happen? Young adults who go to college typically have parents with more income, more education, and a greater concern with education. Moreover, these young adults typically have done well in high school. They have personal qualities that allow them to succeed in school and possibly ambition, discipline, and intelligence. So it is hard to think about a study where you can measure everything that will be relevant and everything that will make your comparisons exactly fair. So when you observe higher incomes among those with college education, those with, I should say, Catholic school education, that leaves you in doubt about the cost caused by education, by many distinct attributes that put them through schools. So next a bullet point here. Okay, so I have made an argument that this comparison may be biased. The direct comparison of Catholic school to public school may be biased. But just because they may be biased, it should not immediately dismiss this comparison. This direct comparison can actually be insensitive to large biases. We showed in our paper this fact, or we observed this fact by calculating design sensitivity. Let me come to comparison 2, where you use being Catholic or raised Catholic as an instrumental variable. So this is a typical picture for the instrumental variable. For raised Catholic being an instrumental variable, there are 3 main assumptions that are required: the exclusion restriction, the association, and the ignorability. And people can use other terms for those. So just to walk you through this picture, it says that raised Catholic should encourage you to go to Catholic school, but it should not have an effect on earning in any other way than its effect on going to Catholic school. And it also says that raised Catholic should be a somewhat haphazard assignment. So it should not be associated with some unmeasured variables, which can also affect earning. Living near Catholic school has a similar picture. It should also encourage going to Catholic school. It should not affect earning in any other way than affecting your chance of going to Catholic school, and it should not be associated with any unmeasured variables, which can be associated with earning. Okay, so I'll note here that validity, if you take both of them together, living near Catholic school or raised Catholic together, does not immediately imply that you need weaker assumption than any one of those. So in our study, we took a data from Wisconsin longitudinal study, WLS, which consisted of about 4,500 students who are high school graduates in 1957. And we looked at their earning at the age of 35. So in this table here, I'm showing you a summary. In this summary, you will see two sets of columns of 3. In the first column, you have urban and rural, by which we are distinguishing whether they're living near Catholic school. So urban areas tend to have more Catholic schools, at least at that time, 1957. The second column is for religion, Catholic or non-Catholic, and the third column is for which school they attended, Catholic school or public school. Over here, you will see 22% of the urban students went to Catholic school, and 6% of the rural students went to Catholic school. In religion, among the urbans, 44% went to Catholic school, and no one, at least in our data, went to Catholic school. In the rural areas, the numbers were different, but the direction of association was the same. So we considered three comparisons using the same study. In the first comparison, we stratified on urban, rural, and religion, and compared the two types of schools, Catholic schooling or public schooling. So that's the third square here, third rectangle here. So that's the first comparison that stratifies on religion and urban. The second comparison is on religion, comparing Catholics and non-Catholics within the urban areas and within the rural areas. The third comparison is between urban and rural. So these three comparisons are connected to the three implications or three testable implications of our causal hypothesis we wrote about. And a generalization of the proof I showed you will show you that these three comparisons are nearly independent. They also depend on separate assumptions that, just as I mentioned over the last few slides. Okay. So of course, our study stratified on other variables like IQ, parents' education, income, and occupation. And for this purpose, we used the R package blocking challenge. Okay. Now I'll go one step beyond it, and I'll see what more can we do with these three comparisons. So these three comparisons will be valid under certain assumptions, but we can relax some of those assumptions. For example, we can allow biased assignments using sensitivity analysis. So in a sensitivity analysis, or any sensitivity analysis, in one way or other relaxes a doubtful assumption. It's not same as replacing that by some other assumption. So we can gradually relax the assumption of no unmeasured confounding. And you can use a different type of scale from me. But what I used is Rosenbaum's gamma scale, where in a single comparison, you can have a gamma, which measure how much bias is possible due to unmeasured confounder in your analysis, in your comparison. So gamma here would mean that between two people with the same measured covariates, the maximum odds ratio that one gets treatment rather than the other because of unmeasured confounder is gamma. So gamma equal to 1 means there is no unmeasured confounding. Those two people, after adjusting for measured covariate, are getting the equal probability of being in the treatment group. Gamma equal to 2 would mean something similar to what I showed in the example, that one of them has double the odds of being treated just because that person has a higher or a lower value of the outcome. So measured covariates are not sufficient to explain gamma equal to 2. So given a comparison and given a value of gamma, we cannot calculate the p-value, but we can calculate the maximum possible p-value when the bias is at most gamma. So what we can say from that is the following. If this p-value upper bound is still small, if the p-value upper bound is still small, then we know that the bias of gamma or less is not sufficient to refute an evidence that we have. So in our study, we have 3 comparisons and we can discuss 3 gammas. And this is slightly notation heavy here, this slide. You have P1, P2, and P3 in Roman 1, 2, 3. And associated with them, you have defined gammas, gamma 1, gamma 2, and gamma 3. So gamma 1, gamma 2, and gamma 3 here relaxes your assumption of ignorability or no unmeasured confounding in different ways. And when you are talking about independent comparisons or evidence factors, what should be true is, given any gamma 1, gamma 2, and gamma 3, these 3 numbers on the left should be independent of one another. And that's exactly what you can prove. What you can prove is, if Catholic schooling had no effect, and if the 2 instruments satisfied partial exclusion restriction, it's something little relaxed than the exclusion restriction, and if the biases due to unmeasured confounding were at most gamma 1, gamma 2, and gamma 3 in our 3 comparisons, then these 3 p-values are indeed, or maximum p-values are indeed nearly independent. So just for completeness, by near independence, I mean the following mathematical statement. I won't go for it. Okay, so here is the result, the first set of result you can produce from that. The first set of calculations using our 3 comparisons will give you the maximum p-values. For example, in the highlighted over here, it says, if you assumed that there was no unmeasured confounding in any of those comparisons, then all 3 p-values are small. Okay. But you can go beyond it. So you can look at some relaxation of gamma equal to 1.1 in all 3 comparisons. And then you can get the p-values which are larger than the previous ones. So how do you read this? You can read it in the following way. The third comparison, if you remember, is comparing urban and rurals. And this comparison remains insensitive up to bias 1.25 because this p-value is still less than 0.05. The other two comparisons are not insensitive for any bias level more than 1. Okay, so this is one way to strengthen your evidence. Rather than reporting just this one row, you can report the whole table and you can discuss whether what you saw when there was no unmeasured confounding still remains when you relax that assumption to a moderate extent. So I'll note here that gamma equal to 1.25 can also be interpreted in a different way, which says that there exists an unmeasured confounding that can double the odds of being treated and doubles the chance of a higher outcome. Okay. Now, this is, as I said, is the initial set of results you can get from it. But because we are doing evidence factors, we can actually get a lot more from it. And that will be my fourth point. How do you integrate the evidence from evidence factors? So one way to think about it is the following. Although you are using the same data, we are using the same study to do 3 comparisons, our theorem says that they are nearly independent. So we can treat them as if they are coming from different studies. And we can use meta-analytic tools to combine them. For example, we can use Fisher's p-value combination methods to combine the 3 p-values. The one we use is slightly more general than Fisher's. So we use Jekin et al.'s truncated product method, which emphasizes more p-values which are smaller. So it takes product of p-values less than a cutoff, and the null distribution of this becomes a mixture, binomial mixture of gamma distributions. Okay, so I added an additional column to it where along every row, I have combined the 3 p-values using truncated product method, and I got a combined pooled evidence. Now, according to this pooled evidence, we still have insensitive results up to 1.2. At 1.25, the p-value is high. Okay. Now you can do even more than that. You can ask, can you quantify how much of our evidence, if we are doing 3 comparisons, depends on just a single one? Probably we don't want to use just one comparison to conclude something, since we are doing 3 comparisons. So more specifically, we can ask, assuming moderate amount of biases in the comparison, so assuming some gamma, how much evidence for the effect of Cauchy schooling is provided by at least 2 out of 3 comparisons? And that we can answer using a similar meta-analytic tool, which is called partial conjunction analysis. In a partial conjunction analysis, we can create a second column, which essentially is calculated using the following method. So along every row, you take the 2 p-values which are high, and then you combine them. So 0.0008 here comes from comparison 1 and 2, because of the 3 here, these 2 give you the largest 2 p-values. So you'll see at gamma equal to 1.2, even though combining all 3 of them, we had an evidence which was still less than 0.05, or p-value which was still less than 0.05. When we emphasized that we need to look at least 2 of them, that goes away. You have a p-value which is 0.34. Okay, and just to be cautious here, we can show by theory there is some geometry in this calculation, so that you are allowed to look at all these numbers at the same time at level alpha, and you are ensured a family-wise error rate control at level alpha. So what conclusion do you make from all of these? The conclusion is not a one-sentence conclusion that we did a comparison and this was my p-value. A conclusion is more elaborate. We conclude that if there is no bias due to unmeasured conformity, that is all gamma equal to 1, then there is evidence that evidence of Catholic schooling effect, and we have 3 independent comparisons. When gamma equal to 1.1, there is evidence of 2 independent factors concurring in finding the Catholic school effect. So I'm looking at this number here. For gamma equal to 1.2, there is evidence of Catholic school effect from pooled test, but the evidence only comes from urban and rural comparison. The inference of a Catholic school effect depends rather heavily on validity of the urban rural as IP. So how do you test the validity of the urban rural IP? So if you look at the non-Catholics, almost among the non-Catholics, almost no one attends Catholic school. So you have a picture which is slightly different. You don't have an arrow here. No one is being encouraged among non-Catholics to go to Catholic school. So if urban rural is valid IP, there should be no effect of urban rural on earning among the non-Catholics. But when you look at the data, among the non-Catholics, median wages were higher in urban areas than rural areas. So it is of concern that our conclusion about the effect of Catholic schooling depends so heavily on that instrument, that one instrument. Okay, so that will be my concluding discussion of that study, and the rest of the few slides I have here is on how to implement. If you want to use evidence factors analysis, how do you do it in your own study? So there are a few pieces here. The first piece is to design, is to create a design from your study that allows evidence factors analysis. So typically in observational studies, it is common to formulate the design as a constraint optimization problem. And the designs you need here is slightly more general here. For example, in our study, we use stratification. So we stratified all on the background variables, and we used our package blocking challenge. In other studies, you can use mesh design, which adjusts for covariates, but uses treatment levels with multiple treatment groups. And you can do that using the R package approxmax. The other part of it was calculating the p-value and p-value upper bounds. And we use the R package senstrat. And a good starting point for those kind of calculations would be this book by Paul Rosenbaum called Observational Studies. So the last slide I have here is the concluding slide. First, in observational studies, both bias and treatment effects can replicate across independent studies. So replication is not repetition. If replication amounts to disturbing the principal potential bias, then a single observational study can replicate itself by performing several independent comparisons affected by different biases. So what do we learn? What can we learn from evidence factors? Integrated evidence factors can give you a strengthened conclusion, but it can also suggest caution. A design that always encourages causal conclusions, a design that cannot suggest caution or restraint, is not a good design. An easy way to publish false causal conclusion is to decline to look for evidence that might reveal bias. And this is my final slide of references. This talk is based on this first paper, and you can look more for the theory of evidence factors in these 3 following papers. Thank you, everyone.